Hello everyone, this is chapter 7, number 84, reassessment number 9. So the problem tells us that when the ball hits the ground, it interacts with the ground for a short amount of time, and it bounces off at a different angle. I broke this problem into 4 different steps just to track it a little easier. So since we know that, for part 1, since we know that the ball bounce and there are 2 different velocities, we can determine that there will be like initial and a final phase to the bounce. So in this, when we keep this in mind, we can go ahead and solve for, pretty much ultimately going to solve for delta p, but we're going to write this equation p initial equals mv initial, and then p final equals mv final. So yeah, so now that we have our little equations, we can go ahead and solve for the vector of velocity initial, which would be it gives us the velocity right here, and it tells us that it's gonna be that when the ball hits the ground, it's like a negative 22 degrees below the horizontal, so it'd be negative 22 degrees, cosine and sine, and these are the x component and the y component, and we could solve for the vi vector for that. We're not gonna completely solve for the vector. We just want to break it up into 2 components. So we plug that into our p initial equation right here, and we'll get an x and y component of the p initial. And again, we don't want to solve for the vector pi just yet. That would be like the square root, square root x component squared, y component squared. We don't want to do that yet. So in step 2, we did the same thing with the PF equation. This time it tells us when it bounces, it goes above the horizontal 18 degrees. So here's our x and y component. It gives us the velocities. Plug that into the equation itself, and we'll get the x component and y component of delta p. So, the vector p. So knowing this, delta p vector equals pf minus pi vectors. So we just plug everything in. We had our pi right here and pf right here. We'll end up with this x and y component by itself. And now we want to solve for the delta p vector. So we can square root it. Take that x component squared and the y component squared, and we'll get 2.196 kilograms per meter second. So now that we did this, we can go ahead and plug in to our equation force equals delta p vector over delta t. We have delta p, we just solved that from up there, and we have the time it gives us when it interacts with the ground. Like I said, it kind of interacted for a short amount of time. We'll get 33.78 newtons, which would give us our magnitude of our force, 33.78. I didn't mention this before, but the question actually asks, like, what is the force, the magnitude of the force the ball exerts on the ground? So, yes, this is our final answer, 33.78 newtons. Thank you. Hope you guys learned something.